Okay, so I saw an interesting problem on the interwebs that I would like to share with you. Some of you may have already seen it. And you can see the stuff that we did in the last video on the back. Just ignore that because I'm using pen so you can see it a little bit better. Okay, so we are gonna now be working with okay, so Herman, the human cannonball. Some of you already recognize this problem. Herman, the human cannonball, he is being launched out of this cannon. Let's see if I can draw. It's a very bad cannon, but oh well. That's our cannon. Don't think too much of it. So, and he is being launched out of the cannon. And he's going to be doing that at 30 degrees. 30 degrees off the ground. The cannon is aimed 30 degrees off the ground. And his initial velocity is 26 meters per second. Okay? And what we're trying to find out is how long or how far horizontally will he travel. And to do this, we need two kinematic equations. We need velocity is equal to distance over time. Okay. And let's put an arrow over that because we know that velocity is a vector from the very first video that we did in this series. And we represent vectors with an arrow or a line over the top of it. Okay? So equals distance over time. And then we also need the kinematic equation. The final velocity is equal to the initial velocity plus acceleration times time. And you'll see why we need these two in a minute. Let's just box these. Okay? You'll see why we need these in a minute. Okay? So first we need to find the components. Okay? So we didn't talk about this at all in describing motion. I probably should have done that. But so vectors, let's say that we have a vector and it's going this way, okay? That's a vector because it has both a direction and it has a magnitude. Let's say it has a magnitude of 5. This vector will have component vectors, which will be, it's basically going to be the Pythagorean theorem, and it's going to be this vector squared plus this vector squared. Or, I mean, the magnitude of these two vectors squared. If you just consider them vectors, you could just say that this vector plus this vector. This is vector 1, vector 2. Vector 1 plus vector 2, because they're going along the coordinates, okay, equals vector 3, which is 5 in magnitude. We're not going to solve that because that's irrelevant to this problem, but I'm just introducing you to the concept of component vectors. So what we need are component vectors for this, okay? So let's draw a triangle to represent the system, okay? Let's make it nice and big so that you can see it. And here we have 30. I don't know if you can see the 30 very well. Let me just scoot this up maybe. And I don't know if that helps, but this is 30 right here. Okay, 30 degrees. And then the hypotenuse is 26 degrees, and we know nothing else. So for those of you who have not taken any sort of trigonometry at all, I have to introduce you to, or remind you of sine, cosine, and tangent. Okay, so sine of theta, where theta is just the degrees right here, is equal to the opposite side over the hypotenuse. Okay, so like in this angle right here, this side will be the opposite, the velocity, the y component of the velocity over 26. Why is this in degrees? It's not supposed to be in degrees. 26. Okay, and then cosine of theta and this is why people say SOHCAHTOA, because SO, which is written as SOH, is sine is equal to opposite over hypotenuse. Ka is cosine is equal to, God, this is so blurry, I need a new camera, seriously. But cosine is equal to adjacent A over hypotenuse. So the adjacent one is this right here, the velocity, the x component of the velocity, which so is equal to adjacent over hypotenuse, right? But we don't need tangent here. Just to let you know, tangent is SOHCAHTOA, so it's opposite over adjacent. Okay, but cosine of theta is equal to adjacent over hypotenuse, so we're going to be using cosine, and we already know the theta, right? So we take, and we already know the full vector, the actual magnitude of the vector, not the sum of these two. Okay, so what we're going to do is we're going to take 26, and we're going to multiply it to find the y component, because sine of theta is opposite, so we're going to be finding the part opposite of the angle, which is the y component. So it's going to be sine 26 times sine of 30 degrees. Okay? Times sine of 30 degrees. And that's going to give us our y component. I'm going to get my calculator out for that in a minute, but just hold on. And then we're going to have 26 times cosine of 30 degrees is equal to our x component of the velocity. Okay? And then we're going to plug these into our calculators. Hold on, let me just go get my calculator out of my backpack. I will be back in a sec. Okay, I'm back and I have my calculator. Let me just turn it on and use it. Okay, okay, so what do we say? We say that we're going to take sine of 30 degrees. So let me just do that. Sine of 30... Wait. Sine of 30... No, God. I'm still not used to my calculator. Doesn't make any sense to me. Okay. Yeah, because I don't think that there's any way to just set it 2 degrees or radians, which is kind of weird. But oh well. And then we're going to multiply sine of 30 by 26. And we're going to get 13 meters per second for the y component. So let's write that down. 13 meters per second for the y component. And then now let's find for the x component, which is cosine of 30 times 26 meters per second. So that's 22.5, or approximately 22.5 meters per second. And that's our velocity in the x component, okay? So luckily for us now, we have the velocity in the y component, which is what we're going to need most immediately, because where do we put it? Oh yeah, right here we showed the kinematic equations that we would need for this problem, and I'll show you why we need the first one, this one, right now, okay? So what we're going to do is because right now we're trying to solve for time, because in the second kinematic equation, we're going to need or no, we don't need this one right now. That's the wrong one. We don't know distance yet. We don't know how far it's well, that's what we're trying to find out, but we don't know the time, how long it's going to stay in the air. So we need to use this one, not that one yet. Ignore that. We're using this one right here. Okay. So right now we're trying to solve for because we're doing this. So first we're going to use the horizontal thingy right now, and we need to find time. So we know the initial velocity is going to be, so actually let me just graph this, okay? So let's say that we had this, and then the guy, Herman is his path is going to look something like that, right? And so let's start by, I think that the best way to do this is to find how long it takes to get to this point, because right here the velocity is going to be 0, because we're looking at the y component right now. So in the y direction, the velocity is 0. Okay, in the x direction, the velocity is pretty much the same. But in the y direction, going upward, he's not accelerating, or he's not moving upward anymore at this point. So that is where the final velocity is going to be, and then we're just going to multiply that by 2, because then we should get twice the amount of time to get here, right? Everybody agree? Good. So now what we're going to do is we are going to take the, so we concluded that this is going to be our final velocity here, final velocity, because this is symmetrical, so we can just multiply it by 2, okay? So we got our velocity final right here, and then which is equal to 0. And our initial velocity, we already concluded, is, well, because we're looking in the y component, it's 13 meters per second, because we're just looking upward. So 13 meters per second squared, or not squared, excuse me, just 13. Shut up. So the 13, let me just angle this so you can see it a little bit better. So we got, wait, what am I doing? Oh, I forgot. Okay. Now I've got it. So now we're just going to take this equation equals vi plus at, and we're going to isolate the t, because that's what we're trying to find, okay? So we're going to subtract the initial velocity from both sides, which is this, is equal to acceleration times t, right? And then we're going to divide both sides by a. So we got the final velocity minus the initial velocity, right? I didn't write that there. This is initial velocity. Initial velocity, in fact, this is, my camera is so blurry that you might not be able to see this, but whatever, is equal to t. But we have to divide this by a. Okay, so it's so blurry. Oh my god. What are we going to do about that? Push this back, maybe. Yeah. So hopefully you can see it a little bit better now. This is t, not a b. This is a t. So now let's just plug in the numbers. So we know that the final is 0, and 0 minus the initial, which is 13. So that's going to be negative 13, and a, because we're doing it horizontally, the acceleration, or no, vertically, the acceleration vertically is going to be gravity. So that's going to be negative 9.8, because it pulls you vertically downward, and so the negative denotes the downward motion. Positive is up, negative is down. Okay, so we're going to take negative 13. So that's negative 13 divided by negative 9.8 equals t. And what is that? Well, let's get out our handy dandy calculator. Crap, it's not even on. Negative 13, divide that by negative 9.8, which is equal to 1.33. Approximately 1.33 seconds. So let's just write that down. This is equal to 1.33 seconds, okay? That's not secant, that's seconds, okay? So there is our time, but that's not what we're trying to find. We're trying to find the distance. But look at this, up here, right there. Now we get to use this equation, because now we know the time. So what we're going to do is we are going to take, because we're trying to find distance, okay? So we take the velocity, and because now we're looking at the horizontal direction, because we're trying to find his motion horizontally now, instead of vertically. We're disregarding vertically. So we're going to take the horizontal component vector, which has a magnitude of 22.5 meters per second, right? Because we're looking at it along the x-axis. 22.5. All right, so 22.5, and actually let me write that equation up there, down here. So just so you can see it, it's pretty obvious. So velocity equals distance over time, right? So 22.5 is our velocity in the x direction, and we're only looking at the x direction, which is equal to distance over 1.33. 1.33. Okay, right. So now what we're going to do is we're going to multiply both sides by 1.33. So I got 22.5 times 1.33 is equal to, hold up, let me get my calculator out. 22.5 times 1.33, that's, no, 22.5 times 1.33 is, this says 29.925, but I know that's not the right answer, or it shouldn't be the right answer. So let me just go back and check my work. I apologize. We forgot to double the time. Right? We forgot to double the time, which actually isn't that bad of a problem. So we just multiply 1.33 times 2 equals 2.66. So we're just multiplying this time by 2, because if you don't remember, we just took the final velocity right here. But this is only half of the path, so we have to multiply this by 2, which doesn't actually make this that bad, because, actually, yeah, it does. No, it doesn't. Okay, so what we have to do is we have to multiply this by 2, which is 2.6666 meters per second. So 2.66, right? Because we forgot to multiply that by 2. That's what I did wrong. I'm sorry. I'm doing this as I go along, and I'm half asleep. So don't judge me. So we're going to scratch all this out, right? Because now we know that the actual time isn't 1.33, but it's 2.66. It's double that. So we're going to take 22.5 times 2.66, and then this will give us the actual answer, which is 59.85. That is the actual answer. See, we forgot to double this because we're supposed to, because this only went half the path when we considered the velocity was 0. If you absolutely wanted to, you could totally just do negative. You could totally just ignore this whole doubling step. I probably should have. It would save me a lot of time to ignore all this doubling and just do the negative 13 right here and just consider the final velocity here instead of up there. I decided to take the hard way, and that's my fault, and I'm sorry, but oh well. I hope that you guys get the basic gist. My name is Yuichi Greywright from, oh, and this is meters. Okay, my name is Yuichi Greywright from Salutary Spade Science, and I am signing off now.